0.5 moles of O2 and 0.12 moles of N2 are placed in a 2-liter container at a temperature of 27 degrees Celsius and a pressure of 773 kilopascals. What are the partial pressures of each? So in this question, we're going to use Dalton's law of partial pressure, which really just says if X amount of one gas is in the container and Y amount of the other is in a container, then the pressures divide up by X and Y. So we'll see that 0.5 moles of O2 is a much bigger number than 0.12 moles of N2. So we should assume then that there'll be a lot more of the pressure associated with O2 than N2. And so let's write that out now. So number of moles of O2 is 0.5 moles, and number of moles of N2 is 0.12 moles. So how do we figure out the partial pressure of each? Well, we simply need to put in the number of moles into the ideal gas law formula, PV equals nRT, rearrange for P, and then solve. So let's do the O2 first. nRT over V. We know that the temperature is 27 degrees Celsius. However, we cannot use Celsius in this formula or in any of the formulas, so we need to convert that to kelvins by adding 273, which gives us a temperature of 300 kelvins, and the volume is 2 liters as given in the question. So let's solve. 0.5 for the oxygen times 8.314, which is what R is always when we use these units, times 300 Kelvin, all divided by 2 liters. And when we multiply through and divide by 2, we get a pressure for the oxygen of 623.6 kilopascals. So note that the total pressure in this question was given at 773 kilopascals, and that most of that, 623 kilopascals of it, is associated with the oxygen, which is what we would expect by looking at the number of moles of each of the oxygen and the nitrogen. So the leftover pressure then, I'll have to go with the nitrogen, but let's solve it the long way anyway, just to prove that. So we'll put in the numbers for nitrogen, which was 0.12. Everything else remains the same, since it's in the same container, in the same conditions. All divided by 2, and we get 149.7 kilopascals. So that is the partial pressure of each of these gases. Note, if we add up 623.6 and 149.7, we get roughly, within rounding errors, 773 kilopascals, which is the total pressure. And also note, we didn't need the total pressure in this question. It was just given in this case so that we could check our answer and see. A word of caution on Dalton's law of partial pressure: they're not all PV equals nRT type questions. Any formula with pressure in it can be used, you can use the Dalton's law of partial pressure with it. It just means how much of the pressure is associated with one gas compared to another gas, and if you put the two together, you can get the total. In fact, you should try adding up 0.5 and 0.12 moles to get 0.62 moles, and put that into PV equals nRT, and you should get 773 out, because both of those gases together make the total pressure.